Okay, so we're starting with graphing now. Essentially what we're going to see is what does calculus offer us in terms of drawing graphs that we didn't have before. If you remember from last course, basically with a polynomial, quadratic functions look like this, either a parabola opening up or a parabola opening down. Cubics start down, might have a little twist in the middle, and continue on up. Quartics, you can see them there, and quintic functions are here. The one thing to recognize is essentially in a second power function, we have two sections to the graph. We have the increasing section here and then the decreasing section, or the decreasing section here and the increasing section afterwards. Essentially, there's one turning point, one change in direction. This one's less obvious with the cubic, but obviously the second one here, you can see it clearly. There's one section here where we're decreasing, one section where we're increasing, and another decreasing. Two changes in direction. So the power is 3. There are two changes in direction, 3 distinct sections. Quartic continuing the same pattern, 1, 2, 3, 4 sections, 3 changes in direction. And quintic, 1, 2, 3, 4, 5. So an increasing section, a decreasing, increasing, decreasing, increasing. 1, 2, 3, 4 changes in direction. Okay, so that's just kind of reminding us what the graphs look like, so we have a basic idea of in our heads of where we're going with these. So pre-calculus, what did we know? We knew the basic shapes, we just saw them. The maximum number of sections or changes in direction, we just sort of mentioned as well. The number of sections is equal to the power. The number of changes in direction is 1 less than the power. To determine the x and y intercepts, what we'll call key points for now, we sub y equals 0 and x equals 0 in. So sort of get those nice points for graphing purposes. And in functions, when we had to determine end behavior, we tried to figure out what was going on. It looks like my graph here is a little bit messed up, or I must have changed the size of this. This should say determine end behaviors. We can sub large values of x in to see whether we get negative or positive. In other words, whether we're approaching positive infinity or negative infinity. I'll fix that before I print it out. So what does calculus add for us? What we've been dealing with mostly is derivatives. And you want to remember that the derivative of a function is a way to find the slope. And so this will allow us to figure out whether we have that increasing or decreasing section of a graph. So if I know the slope here is positive, then I know I'm increasing. If I know the slope over here is negative, I know it's a decreasing section of the graph. And that, of course, will have to do with the fact that the derivative of 0, derivative of 0 indicates maximum or minimum. Once we know where the maximum and minimums are, if we know whether our slope is increasing or decreasing on either side of that, we can determine whether we have maximums or minimums. So I'm just going to go through one example here. So this is sort of the steps that I intend to take. Given the fact that this is my starting equation, I have to sketch it. I want to have a basic idea of the mental idea of the basic shape. It's a 4th power, so a quartic expression. The value out front is not negative, sorry, it's positive. So I know that my basic shape will look, something like a W. My intercepts I can find by subbing in y equals 0 and x equals 0. Critical points. Now, from the previous page, critical points are how we refer to things that will be maximums and minimums, so kind of combining the two. So I'll have to make the derivative equal to 0 to find those. And then to determine whether an actual point is a maximum or a minimum, knowing that this point right here is a critical point doesn't help me determine whether it's a maximum or minimum, regardless of whether it's bigger or smaller than another critical point. I guess it does to some extent, but really, if we have just a single value, what we need to be able to do is determine, are we increasing to get to that point or decreasing to get to that point? And so that will be the last step here. So I'm going to pause this and put up some numbers. Okay, so just a quick note, I've changed my equation. I had intended to take the +2 off just so I could go through all the different steps. The +2 kind of made finding the x-intercepts basically impossible without technology, so I apologize there. So first thing I'm looking for are the intercepts. If I can find them by regular math means, I will. If I need to punch them into a graphing calculator or something, I don't need to worry about that. But if it's something I can solve for, I should be able to do that. I should do it. So the first intercept, the y-intercept, is always the easy one. Plug in x equals 0, and we get that y equals 0. That's fair enough. To solve for the x-intercept, we make y equal to 0. So we have 0 equal to the equation. If we factor out the x squared, just a second, I'm going to pause here. Sorry, a couple of interruptions here today. So we said we need to factor out the x squared. Remember, this is something that I noticed on the last test. A few people, instead of factoring out an x or an x squared, divided it out and thought that it disappeared. The only time we can do that is if we have an equation for sure, but we also are just factoring out a constant. 2 times all of this doesn't change the value of x, but x squared, an unknown value here, is one of my solutions. Now it turns out that in this case, the x squared being 0, if x squared is 0, then x is 0. It happens that that is the same solution as over here, but it certainly doesn't have to be that way. So if you're looking for intercepts, you must consider the x squared as one of the solutions. Now, in determining the second part, I'm looking to factor this. I can't, and so I'll use the quadratic formula. And those of you that have had me before know I always put in brackets when I'm doing substitution. So -4 is the b value. Oh, rats, I messed up. 1 and -8 are the other two values. And so when I get down here, this is +4 now, this is +4. I think the answers are right though. So those are 3 points that will go on my graph. The next thing I'm interested in are the critical points. So those turning points, basically. Critical points are turning points. They are what will be the maximum minimums eventually. So my derivative, hopefully by now I don't need to go over that too much. And so to find the critical points, we'll make that equal to 0. So again, I guess I'll pause so not to take up too much time while I... Okay, so finishing up here, we found our derivative. Making the derivative equal to 0 allows us to establish where the critical points will be. And so in this case, 0 equals exactly that. I factor out the 4x. Note here from what we said before, I could divide the 4 out and have it disappear, just have x times, and then this term can be factored, x minus 4, x plus 1. And so x equals 0 is the solution for this. X is 4 here, x is -1 here. And of course, this is where we then have to establish what the y values are. For the intercepts, we knew the y values were 0 because that's where we were sort of starting with. In this case, I need to know what the y values are so that I can plot the points. And so back into the original equation, I'm going to sub those x values into my original to determine what the y values are that go with it. So again, the 0, we already know 0, 0 is the point, so plug in the 0, and I get 0, 0 as one of my critical points, one of my turning points. -1, when x is -1, plugging that into the original, we find that y is -3. And when we put the 4 in, we find that y is -128. So last thing then, we need to establish whether those are maximums or minimums. Once I know where those zeros are, -1, 0, and 4 in this case, I need to basically establish what's going to happen in front and behind each of those. And so to the left of -1, I want to figure out, I want to test each value, test the values in each domain to determine whether positive or negative. And the magic word is slope. So we're testing in f prime to determine whether or not these values are increasing or whether things are increasing or decreasing in each of these ranges. I'm looking for something less than -1, so something like -2. So I have -32 here. I have -48 here. So clearly, in this domain here, I have a negative value. So that means I'm decreasing to hit the -1. After that, if I test a value in here, I would find that I'm increasing back up to the 0. If I've increased to the 0, I've clearly decreased down to the 4, and I've increased beyond the 4 by putting in positive numbers in all these spots. And so that tells me what my graph will look like. And so what I've got now is I have my whole graph kind of planned out. I have critical points, I have intercepts, and I know whether I'm increasing or decreasing to get to my various critical points. And so essentially then I would just put up a sketch. Now remembering the one number was +4, or the 1 point, sorry, was +4 and -128. I can't do a perfect job, but I'll do a pretty good job. So let's see, what points did I have? I had 0, 0. I had -1.456, so right about here, and 0. I had -5.456 and 0. And then I also had -1, -3. And so -1, -1, 2, 3. Try to keep some perspective here with the fact that this is supposed to be -128. And then the last thing I determined was my graph starts off by decreasing to the -1. My graph will decrease to the -1, increase to the 0, decrease to the -4, come back up through that, and continue on outwards. Okay, so that is the basic look of my graph. And if you want to see more or less what the graph looks like, you can always put it into Desmos. And the points, when I click on the graph, it gives me the point 0, 0, -416, 5.464, -1, -3, and so on.